Go. Okay, so I think today might be a half-length lecture, and then we can move on and kind of talk about the project, I guess, for a couple of you that are finished with lab, well, the I2C lab, I forget the numbering. I'll talk about the complete lab. I almost have it written up, so I'll post it hopefully today, if not tomorrow, so that you can have an idea of where you're going with this. I would like everyone to know that I do have the intention probably of not coming back to class after Thanksgiving break. We will probably just try and get everything up. I'll still post some more videos after that, and we'll finish up the lab. I will still hold labs so that anyone that wants to come can, but I just don't want the COVID thing to get too out of control. But I'll post an announcement once I get exactly the plans for that one. Because even, when is the last day of class? Like the December 4th or something? So yeah, so there's maybe 2 weeks after Thanksgiving break anyways. So I'll look at that. I will definitely be available in labs and on Zoom on that. So we'll see that go. The remaining topic that we have left after today is just, well, there's kind of two, but they fall into the realm of testing. So different other kinds of testing that we haven't really talked about and how do you design for testing. And I'm working out the best way to approach that still, just because the way the book does it is a little outdated. So working on that. For today, we'll be talking about something that's called, well, of how do you cross clock domains. So a clock domain is, simply put, what speed is your master clock going, right? So our clock domain has always been 100 megahertz, right? We haven't fiddled with changing the system clock at all. We can, but we haven't done that. But let's say that we're in a system like a medical device where power consumption is a big deal. We may not want to have a 100 megahertz clock running over the whole thing because that consumes what we would call dynamic power, right? So the clock changes, every time the clock changes, it takes energy to change that clock. The faster the clock runs, the more energy we burn. So maybe one of them has to run fast, right? So let's say, yeah, part of the system that is doing all of the thinking, right? Say it's doing like image processing or something. That needs to run fast. But you may have other parts of it, like the control logic, like if you have a little remote, humans don't operate quickly, right? As far as compared to computers. So what we want is maybe something that like a 1 kilohertz clock domain plugging into a 100 megahertz clock domain. Or maybe not that extreme. Maybe you're trying to interface with VGA, which I believe runs at 25 megahertz. And your clock domain is 100 megahertz, right? And you need to pass data between the two, right? So there's lots of reasons that we might have multiple clock domains. It could be that we have two different devices that are communicating and they go at different speeds. It might be one device has different sections of that FPGA that are dedicated to different clocks. So when we do this, you have different challenges, whether you're going from so passing data from a slow domain to a fast domain, or from a fast domain to a slow domain. There are different challenges depending which direction that you're going. And I haven't done this lecture, right? Okay, just making sure, because I did this in the other one, I want to make sure I don't get this mixed up. So we'll build up to something that I've been talking about all semester here, that's called a FIFO, but we'll talk about this more step by step and what these kind of challenges are. So if we start out going from a slow domain to a fast domain, right? This is the easy situation because we'll just use the fast domain. We'll look at this from the perspective of the fast domain, and we can recognize that as long as we're even twice as fast, we're not going to run into really any issues as long as we write some fairly simplistic logic, right? So that's not a good. This will be my fast clock. This will be my slow clock. And my slow clock, we'll say, is much slower. We'll go 3 times. Yeah, and we'll do it this way. 1, 2. Okay. So I have a fast clock and a slow clock, and they're kind of synchronized, right? So the rising edge is happening at about the same time here. And so this might happen if you're using the fast clock to generate the slower clock, or using the same PLL. So PLL is a term you'll hear me use on occasion, maybe used it before. It's called phase locked loops. They're kind of outside the scope of this, but they're a method for generating different clocks off of a given clock. Okay, so now let's think about the data. What we don't want is to have a situation where these 2 clocks, where we're trying to sample the data, right? So we're going from the slow to the fast. So the issue could be that if I update the data in the slow domain here and try and take it in the slow domain or in the fast domain at that same time, we have this metastability issue, right? So what we could do, there's a couple different ways that we can do this. So one of the kind of brute forcey ways is we look at this, and on the rising edge, we say something like, on rising edge of clock, if the last rising edge of clock was low, and the next rising edge of clock is high, then we know that the clock happened here and we can update on this clock, right? So we can just use the fact that the faster clock runs faster than this one to watch this clock to know when data here is valid. The only time it's not valid is the setup and hold time, right? And we can just make sure we're outside of that window and we're good to go. Now that requires us to be 3 times faster, essentially. If we're not 3 times faster, you need to be careful, because if you were only 2 times faster, well, that actually works as long as you're like 2 point something times faster. It kind of can calculate based on the setup and hold. As we get to just 2 times faster, that can be an issue. So we have a nice trick that we've learned before from debouncing, where all you have to do is take 2 let me go this way. Can this be seen? I should try and find a different color. That's garbage. Try this one. Okay. I don't know if that's any better, because it's not. There we go. All right. All right, we have the slow clock and the slow clock domain. It updates. We know that there might be a race condition at this output, right? When this updates versus when this updates. that creates a region of, flashback to this, metastability. And then when we clock in again on this fast clock, we're no longer metastable. So we have an output, because this one kind of just doesn't know what it is. This one has to, because it's in the same clock domain. They're synchronous. So all that we have to do, we talked about the same idea for doing the for debouncing, and 2 flip-flops is enough. And all that means is we have to wait for one fast clock delay, one extra fast clock delay, instead of just plugging one into the other. Done, we're done. So like I said, slow to fast is fairly easy. Now, if we want to go fast to slow, we have a couple of different choices that are, they're okay, right? So when we go from fast to slow, we again probably want to use kind of the fast clock as our reference, because it's easier to execute when we're thinking in like the fast domain. And so what we would do from the fast clock's perspective is, instead of doing, so we're going from fast to slow now, right? We know that the slow clock just can't keep up. So what we could do is build some sort of register in the fast clock domain that its output updates after however many clock cycles I need it to be, right? So I create some sort of register and I say, we count 1, 2, 3 clocks and I update. Well, I guess on this one we could do a lot more than that. We'd have to do a lot more than that, right? They're slowing. So we go 1, 2, 3, 1, 2, 3, 4, 5, and then update it essentially. And then this would clock in that data, and then we rinse and repeat, making sure that these setup and hold times are consistent. Now, if these clocks are not synchronized this, right? So if they're not directly divisible by each other, we need to be careful, because you could end up in a situation where your clock drift gets you in trouble. If you do that, it's sometimes helpful to generate kind of an intermediate clock that's a little bit faster than your slow clock that is directly divisible, and then do kind of a handoff to make sure that they're controlled. That's a little bit extra effort, but the general idea of going fast to slow is just drag it out for whatever the appropriate amount of time is. Interestingly, the faster the fast clock is compared to the slow clock, the easier this gets. This gets illustrated in your UART lab, right? This is essentially crossing clock domains, because you're going from your 100 megahertz to 100 kilohertz, I forget the exact number, 115,200, right? You're crossing clock domains. You're just counting these, and you can calculate the clock drift that you have, right? So clock drift, I believe I mentioned this a week ago, maybe a little longer, which is the idea of, as I start putting out packets of data, so in the case it's UART, I'm trying to start by transmitting in the middle of one of these bits, and then we update on the following edge, right? And if we start to drift, we can drift an entire half a clock cycle minus the setup or hold time before we have an error. So if we have 1% drift, well, we only have half of it, right? So if we have 1% drift per clock, so if we're off by 1% of the ideal, then we can take half of that, because we're centered and we can only go 50% one way, 50% the other way. And then we can kind of subtract out the setup or hold time. And then you can calculate from there how many clocks before you start violating setup and hold times due to clock drift. Now, you can start extrapolating this out to larger bit numbers, right? So if I'm sending out 100 kilobytes of data, suddenly 1% clock drift is a problem. But an 8-bit UART packet is like 1% drift, who cares? So obviously you can calculate what the clock drift matters, and you can come up with more advanced algorithms that adjust for clock drift issues. Like leap year, right? You can just kind of wait a little longer, 1 year, throw an extra day kind of thing to offset that clock drift. And again, the faster your fast clock is compared to your slow clock, the easier that is, because the less often it has to happen. Okay, so these are the general ideas of how you would do it if you were doing maybe a one-off. Oh, something I should say to point out, the 2 FIFO, the debouncing method, all you have to do is create like a temporary signal if you actually wanted to implement this. So you'd say something like dtemp, so the temporary data that's held in that metastability region is equal to the output of the slow clock. So we'll call that slow out. And then you say something like fast out is equal to dtemp. Right, so now I've just created 2 registers, one after the other. So that's the actual implementation of the first one. The implementation, of the fast to slow. This is, or sorry, slow to fast. And then fast to slow is just counting. Now we're not going to have to worry about that because these are okay solutions for one-offs. But realistically, we want to be concerned about major data paths, right? When I start pushing in tons of data over and over and over again, we introduce this concept that I keep mentioning called the FIFO. And you have 2 different types of FIFO that kind of serve different functions, but they're both incredibly useful. You have synchronous FIFOs and asynchronous FIFOs. So in both cases, the FIFO, and I'll draw it like this for now. It doesn't really have like a dedicated symbol as far as I know. Actually, let's make this 8. So 3, 5, 6. Okay. So the general thing that we've have an idea of that is easy and intuitive is the shift register, right? Where if on clock 1, I put data into here, then 8 clocks later, it will bounce along and end up here with D0 to be read out. The issue now is I've lost 8 clock cycles. 8 clock cycles isn't really a big issue. But again, what if I'm trying to store data in, I don't know, the hundreds of kilobits range? Then this is not, that delay might actually be problematic. And it has the issue of, and this, every clock, if I want to shift, so if I shift this, but I don't have new data, I get a don't care in and I have to shift that out. Or I can fill it in with bad data, or I can fill it in with essentially don't cares, right? But I have to keep track of that. So anytime I pause for any amount of time, while I'm still shifting, I now get kind of dead zones where I have to now shift out that unwanted data, and that can cause delays throughout the program. So it's not just a startup problem. So the answer to this is instead of using a shift register, we use a FIFO. And the FIFO is going to have 2, well, we'll start off with 2 different flags that essentially, you could also call them pointers that say read pointer and write pointer. So this one says, let's write at 3. Okay, so then I would go ahead and increment my write counter and write the next bit in, call it D1. Then we're going to write the 3rd bit, D2. And then, so I've written 3 bits and now I want to start reading. So my read pointer starts here, right? So I'm going to just number these for a second. 0, 1, 2, 3, 4, 5, 6, and 7. So my read pointer says I'm at 5. I read and then update my read pointer to 6. So read, write. Now if I add 1 to my write pointer, right, it just folds back around because 1, 1, 1, 1, 1. Sorry, this is just 8 bits. So 1, 1, 1 plus 1 is 0. Right? It doesn't store that overflow bit, so it just wraps around. So I write D3, it comes here. And now my write pointer updates to this location. Then I can read, it would update and read, right? And then we're back to this spot. If my read and write pointer are equal, that means that it is empty. So now we can have a new flag that we output called empty, right? And that lets it know that it should not be read from. So with a FIFO, it's important to never read from an empty or write to a full. Because if you do that, well, writing to a full is essentially like erasing the entire FIFO, because now you've exceeded the write situation. So let me carry this through so we can see the why. So I write D3, D4, D5, D6, D7, and let's say I haven't read anything yet. So I go write, 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 write. Now I can use the fact that write plus 1 is where the read is. That means I'm full, right? If I write 1 more to the read, suddenly the read and write are in the same spot, and that's empty. So I have well and truly lost this bit because I've just overwritten it without ever having read it. But it also thinks that my FIFO is empty. So I could lose my entire FIFO. So never read from an empty or write to a full, because you'll end up like you'll end up with errors. If I read from an empty, it suddenly looks like I have a full FIFO that needs to be put out. So those are your 2 big rules. So this is synchronous FIFO. This is a good way of storing data while I'm processing it, right? So I may generate it in chunks, slot it into the FIFO. So I could have a parallel load, just like you have with shift registers, right? I could parallel load and then shift out. I can parallel load a FIFO and shift out, or even load FIFOs in chunks, right? Just like you could do with a shift register. So here we're holding data and transmitting it out. But let's say we have an ADC that's generating bits at 200 kilobits per second, and we're transmitting that data output over a UART at 100 kilobits per second, right? So that ADC is going to have a backlog. We're going to know that we have a limit to the amount of ADC data that we can read that is dependent upon the FIFO storage. Because if that FIFO overflows, we have a problem. So we can read and then wait as it empties out over the slow bus, and then read and then slowly empty it out, right? So we can record in kind of bursts. But to implement this asynchronous FIFO, you can have, well, issues. The way I would strongly recommend implementing an asynchronous FIFO is to use an IP core, right? So just like a memory, they will have a FIFO. You'll be able to tell. So another way of saying asynchronous, you'll also see it called dual clock, because you'll have an input clock and an output clock. And they'll implement some of the ideas like the slowing the data rate and that kind of thing. But just using the IP core saves you a lot of work, because it will just work. You plug it in, hook up the wires like you're supposed to, just like we did with our memory, and now you have a first in, first out, which is what FIFO stands for, and everything works perfectly. Now, I have had to write my own asynchronous FIFOs. Unfortunately, this has happened because at one point I was using Lattice, which is a type of FPGA as opposed to Xilinx or Altera. Lattice is another kind, and they specialize in low power stuff. I can't use an Altera, for example, or Xilinx IP core on a Lattice FPGA. So I have to use Lattices. Unfortunately, we weren't paying for their advanced license. In their case, we didn't have access to the dual clock or asynchronous FIFO. So it is possible that you have to write your own. So I'll start off by pointing out some of the things that you want to be concerned of, and then I may actually assign you to write an asynchronous FIFO. They're kind of fun, but they're also kind of annoying. So the first thing that we want to be aware of is that we do want to use something that we call almost full or almost empty flags. This lets whatever data stream that you know, whatever know that it's maybe running out of time, right? So when I get to, so if my read pointer, well, yeah, let's leave read in place. So we haven't done any reading yet, and my write pointer is here. I might want to output the almost full flag to say that we've only got 2 more bits, right? And that could be an issue. And this could be either direction in the data stream. It could be coming backwards and saying, I need you to stop writing to me, like soon. Or it could be pushing it forward and saying, I need you to start reading out or I'm going to run out of room. And you could have this, you could have a situation where you're prioritizing different tasks and you would use that almost full as a prioritization flag saying this needs to happen now. Like we're using a UART and we're transmitting data out, but say we're sending data out from 6 different ADCs. And maybe generally these read out slow enough that the UART can kind of push it out fine, but every once in a while one of them fills up with a lot of data and we're like, hey, this one needs to go now. Empty flags are the same kind of thing, which is to say that, well, my read and write are almost at that same spot, we're almost out of data. And then it can start saying like, okay, well, maybe I can prepare data to parallel load it, right? So almost empty, almost full, these are useful flags that you'll see on most good to write. Okay. Okay, so then we've had some discussion before about gray code counting, right? Where gray code is binary, except for the only 1 bit ever changes at a time. Now, one thing that can be very beneficial in these types of systems is to help improve stability and performance is instead of counting these indexes as binary, you count them as gray code. And what this does for you is when you roll over, it makes your flag a little bit easier to deal with because if you're binary, you're going from all 1s to all 0s. And if something happens there that's, how do I phrase this correctly? So you can have these race conditions. So say that we're doing the slow to fast FIFO. Let's say that's what we're doing here. Well, if we have a slow to fast FIFO, we can still use that same type of implementation where we do the metastability dual clock or dual flip-flop, right? But what we don't want to have happen is as we roll over, it pulls in one of these random datas in the FIFO, which could happen if I'm trying to update all 1s at the same time. Whereas if it's gray code when I roll over, it only changes 1 bit. So let's say I'm monitoring some signal and I want to make sure that it doesn't change too quickly. So I don't really care about each individual point. I care about like the changes between each points, right? If I have a signal that's going something like this, nice slow ramp, it's ramping up. And this is okay as long as it doesn't ramp up too quickly or too slowly, let's say. If I roll over, but in the middle of that, I take a random address because I'm rolling all ones to all zeros, I could end up pulling in the middle of this. And what it thinks it sees then is so it has the cue to do this, but instead it does something like that because it's pulling from a future FIFO value. Gray code won't do that. Gray code will happily plug along and it changes 1 bit. So worst case, I get this for 1 clock cycle too long or this one clock cycle early, right? So that's kind of the hint if you're doing the designing these yourself is write it in gray, write the indexes in gray code. I think for the moment, I think I'm going to leave the FIFOs there because I'm weighing on the giving you this assignment, making you write a FIFO versus not, because I want you guys to do well on the labs. Where are you guys on the I2C lab? Who here hasn't put it on your board, tried putting it on your board? So just a couple. So, and then who's finished? I know you two, essentially. Anyone else? Okay. Yeah, that makes sense. Okay. Yeah, so let's go and talk about the final lab, since we are kind of moving in that direction. There is one additional lab that I would really wanted to do, which was kind of some simple DSP implementation. For right now, I'm putting that on hold. And what's nice is if we come back to it and everybody ends up finishing the system integration, like if it ends up you guys really understand this, which I think you might, then we can come back in and add the DSP really easily. Okay, so this is digital systems course. We've kind of been building up towards this, but so far we've built modules. Now we want to take all of the modules that you guys have built and are building and combine them into one system. What this system is going to do is basically a data acquisition system. You're going to control everything from a PC over UART. You're going to issue it commands over UART. It's going to generate a signal. You will then have it record that signal and send that data back to the PC. So when I say, like, part of this lab is going to be drawing the block diagram of your modules and labeling the ports to the modules and that kind of thing. Be careful when you have these controllers, right? So you have like the SPI interface and then you have the SPI controller. The SPI controller will be like your module, right? So it's going to have its inputs and outputs, and you're going to tell it when to tell the DAC to write. I am going to have you guys change a few things. You're going to go back into your modules and you're going to make some modifications. One of the things you're going to do is you're going to slow down your UART. Why? Well, it's just arbitrary. It's in order to have a reason to implement a FIFO. So what you're going to do is your ADC, and I'll do this calculation to kind of show you the thinking that you need on these systems. Where did I put the good black pen? There we go. So the ADC is generating data. If I say I want it to create a sample at 3 kilohertz, okay? So we'll say it's 3 kilosamples per second, right? Each sample has 12 bits in it, right? It's a 12-bit ADC, has 12 bits. So then I have 12 bits per sample. Well, that then cancels out and I get bits per second, right? So sample cancel is sample, and then this ends up being 3 times 12 is 36 kilobits per second of data that it's generating. Now, when I convert this to the UART, my UART has 8 bits. So I can't fit all 12 bits in one packet. So I actually need 2 packets, which is okay because we're going to generate some overhead anyways, potentially. And so what we're going to do is our UART packets then are going to have a 2-bit header and a 6-bit, we call this the payload. So we don't have a lot to do with this header just yet, but you could picture how this gets easy, like you could contain which channel the data is coming from. Or it could contain what is it sending you, right? If we had, I don't know, we might have an ADC input and we might have a user interface or something on the FPGA. That's where we use headers, the payload. So really, for every packet of this, for every ADC sample, we need 2 UART samples or 2 UART packets. So we're essentially doubling that rate with overhead. So if this ends up at 72 kilobits a second, and we're sending our UART out at 115 kilobits per second, everything's fine, right? We're transmitting out faster than we're getting new data. But I'm going to switch that around on you, and I'm going to limit your UART to 50K. I can't remember the exact number. It's like 56 something. So that way we're going to get a backlog of data that needs to be handled. The longer we record, the more that fills up. So you're going to need to calculate how big your FIFO needs to be in order to record for X amount of time. And I'll post all of that in the lab. That calculation, just as kind of a way of hints, right, is just going to be looking at how fast do I write new data, how fast do I read data, therefore how fast is it going to be filling up as I transmit.
Is there any reason why we're doing a 2-bit header and 6-bit payload instead of like 4?
Not really. If you want to do it that way, it's fine. I should probably standardize it one way or the other. That's true. It can be useful. Oh no, there is a reason. There is a reason. Let's see if I copied it over. I didn't. I'll put it in the lab that explained it. The issue is in UART, certain characters are problematic because most of your systems that when they record data, record it as ASCII, not as binary. So the easiest way that I'm aware of that you guys could actually save this data and then plot it is just to pull it into PuTTY, because PuTTY can save logs, and then you can load that into Python and then just plot. However, it doesn't work if, say, it sends a delete character or an terminate character or all of these characters that can cause issues. So what you want to use this header for, this is what I remember I was doing, is this is kind of the poor man's encoding solution, where your header will always be, and this will be in the lab, so I may get this wrong, but I believe your header needs to always be 1, 1, because that will put you in the ASCII range of, Well, it has all valid characters. I think it's all lowercase and some other things, with the exception of if your payload was all ones, this in ASCII becomes delete, which is problematic. So what you do then is you use this bit as a NAND of all of these bits, where if any of them are 0, it's 1. But as soon as all of them go to 1, it becomes 0. And then suddenly this 1 0 1 1 1 is a valid bit. So this is just kind of a way to handle the annoying binary to ASCII data handling that a lot of programs do. Yes, you definitely want the 2-bit header in this case. You can set up Python fairly easily if you want to do it another way. So Python has the PySerial library. If you would like to do this the proper way, and I encourage you especially to do this, is use PySerial instead of the log on PuTTY to save that data. We just need some way of saving the data. PySerial makes this pretty easy. Its biggest challenge is when to start and when to stop, essentially. But fortunately, you'll know that, right? So I'm going to give you a requirement, say that like it's going to have to record data at 3 kilosamples per second for 1 second after a given user command. So you're going to have to be the send data either over PuTTY or over PySerial. If you send it over PuTTY, you're going to have to encode your commands in ASCII acceptable format, right? You have to send it an ASCII symbol to get that command out. The commands are going to be things like start waveform, stop waveform, start recording, stop recording, change input. I want to use switches instead of the DAC, right? I want to display the current ADC value on the lights, or I don't want to display the current ADC value on the lights. So you're going to have a fair number of commands that you're going to build up into kind of a usable interactive system that is all controlled via PC. Again, if you're using a PC, you need to be aware of the ASCII to binary conversions, because like if you've seen PuTTY, right? You send a letter. You don't type 10110, right? PySerial will let you send just binary because your FPGA doesn't know what ASCII is. It's completely blind to that. So that's kind of your main push, is bring the system together, have commands to via PC to start the waveform, record the waveform. That's kind of that's the main push of this. Any questions on that? And oh yeah, and bring it back around, because this is going to be higher than your UART. You're going to need a FIFO, if I didn't mention that. I do want to call out that we are going to be doing our exam 3 on the 24th, Tuesday the 24th. That's it. Oh, sorry, no, you guys are on Monday the 23rd. So a week from today, right? Yes, a week from today. And it'll be the same format. You can come in or you can stay home. This is the Monday before Thanksgiving. This exam, did I talk about this last time? Kind of. Yeah, I will post this week kind of a review on material. It's going to focus on the labs. Most. I have to show some content from the microprocessor as just part of the requirements for this class. The main thing that you guys have to take away, right? If you remember the pipeline diagrams, so I posted one homework for the microprocessor one that's pretty mundane. And then the only other thing that you really have to know is, I won't draw out the 2 other stages, right? This pipeline diagram is things like, actually maybe I will. like just start off with the terminology, right? If I have all stages active, it's full. If they're filling, if I'm adding new commands, it's filling. If I'm not adding new commands, it's emptying. And then understanding that like, if I need to pull a new value from memory in this phase. So let's say this command is write immediate to memory, right? And then I have something that's like a command add immediate to this. I would have to be able to ask you, is this allowed? Could I do that? And the answer here is no, right? Because if I'm trying to write immediate, here I do fetch. Well, the big ones are executes go here, right? And so right here, I should be executing, but here I'm not saving that until that moment. So it's not ready to execute that one yet. I haven't finished saving that to memory yet. If I were to wait one clock cycle, I'm okay, one command. So if I might ask something like, if I create data in here, how long do I have to wait until I can add to it, kind of thing. And just give you a series of commands on a pipeline diagram. Or I might ask you that, oh, they're trying to add A and B, or I'm trying to add register this and register that. Let me rephrase that. So I'll give you, say I give you a pipeline diagram, and it says something like, my goal is to add register 5 to register 8. Did this work, essentially? And then just check and make sure that all the data that you had is saved before it's trying to get used. Yeah.
So the release you can do add in your first scenario?
Yes, in this one, yes. Yeah, and actually it's probably the 4th row now that I think about it, because we don't want to, it's still writing. I don't think we want to execute on the same clock cycle that we write. So we do have to wait all the way till here to execute.
So quick question, in the book on page 448, it says that step 5 is only required for load instructions. Is that not true then? The 5th step?
This is true.
Okay.
Ish.
Okay.
The write back, so remind me what step 4 is.
They say that it varies widely between the instructions. Arithmetic and logic can write the computation result for the destination register. Branch instructions must examine their condition and decide to take the branch or not. Load instructions, a memory operation is initiated. For memory store instructions, the data from the second source register is steered to the memory, and a memory write operation is initiated.
Yeah. So does anyone have the notes from last time on what I called this stage? Memory.
Yeah.
Oh yeah, the mem access. So yeah, so the issue is there are many ways to implement the pipeline. So you're not entirely wrong. I could save to memory here, and I'll be very clear in the problem of where it's accessible, but
That's what you'd be reading from memory too, right?
yeah, I can read or write to memory here. So the write back in what the book is explaining is if I'm not saving it to memory and I'm just loading it from that register, then I feed that back around to the next operation. So I guess you're right in here, if I'm doing memory, then as soon as I'm done writing it to memory here, I could execute. So this would be an okay line to do that on if I'm loading from memory. If I'm loading from the register, then I have to wait till there. But always remember that all 5 stages have to execute, essentially. The 5th one is kind of optional. Well, either 4 or 5 has to happen, because otherwise we didn't save it anywhere. We didn't save it into memory, or we didn't save it into a register. So we just lose it. So 4 or 5 has to always happen, but only one of them has to happen. But it doesn't really speed us up any, because it's not like this one can skip its memory and jump ahead into the slot where the memory would be, or the write back would be. So it doesn't really speed us up any, but yeah, the memory might become available 1 clock cycle faster than the output register. Where essentially, if this is your ALU, you can send your output either to memory or back into the ALU to be ready to use it again. It won't be complicated. It's just the main push is to make sure that you get that pipelining increases throughput, but sometimes you have to wait for a command to finish in order to access it. So if I asked the question and I bungled it up and you were like, oh, well, memory's here, so I should be able to access it here. And I was thinking, oh, I wanted you to use write back, so you should here. I'm not even going to mark points down for that kind of issue. It's going to be more about the conceptual of pipeline than it is about a specific type processor. Then the final will also be just, I will just push it out online just like the other ones. I don't even think I'll do an in-class for the final option. It'll just be a do from wherever. The final's longer. It will be comprehensive. It will focus less on the labs. Since I have exam 3, do a lot of questions on the labs. It will bring in some of the conceptual, like the kind of the system level stuff. But it'll flash back to some of the terrible things that we went through before, which is like timing diagrams, and you'll have to do a K-map probably, things like that. Yeah. The exam 3 will be the hour and 15, which I would probably functionally be like an hour and a half. And then the final will probably be, I don't know yet, but it'll probably be the 3-hour allotment. And I might even give you guys more time than that if you want it, kind of thing. I will write it so the longest it could possibly be is 3 hours kind of thing. Yeah, I don't want to suffer too much. And I will post a study guide for that one essentially. I probably won't post a practice exam, but I will post, and I will do a review as well. At least the very least a video review, possibly like a Zoom meet review kind of thing. Yeah, I will try and I will try and do a live Zoom review for that, for the final. For the in person, if you're on video and watching and you have questions after I post the review, then those that aren't here should send me emails for questions. If you are here, we'll have like an in-class review Wednesday. At least part of that class will be in-class review. Trying to think if there's anything else that I needed to talk about for that exam. Oh yes, the other one is if you have any like big questions that are kind of stuck, like if you're really curious about FIFOs, for example, and want to know more about them, you can send me video or send me an email or a Canvas message asking, and I can either make a video specifically for it or can point you in the direction of a good video that explains some of those topics. For material for the exam, if there's stuff that you're just absolutely stuck on, send me an email and I will try and make just like a quick kind of review video of how to do it. That leaves us with 15 minutes. I will wrap that up early so that if anybody has any questions for the lab, the I2C stuff that you're stuck on, the homework that I posted last week that's due Friday, I think. We'll take some time to do that now.